This is a Riemann surface. It's going to help us think in 4 dimensions. We made it by cutting our planes at the discontinuities in our paths and taping them together in a way that made our paths from one plane to the other continuous. Riemann's big idea here is that the domain, the input values of our multifunction, should not be a flat 2-dimensional plane. Our domain should instead be this, a curved surface living in higher dimensional space, a Riemann surface. What's incredible here is what the geometry of our Riemann surface is going to allow us to do. Using our Riemann surface as the input space to our multifunction, we can literally fix all of the problems we've encountered thus far. Our function will be one-to-one, continuous, and our Riemann surface will even help us elegantly explain the weird loop behavior we saw back in part 11. Let's see how. Riemann envisioned these surfaces as sheets covering the input plane W. Our Riemann surface is constructed from 2 copies of the complex plane, and the idea here is that each input value on W lies directly below its corresponding points on each layer of our Riemann surface. If we follow a line straight up from the value 2i on our W plane, we find 2 points that correspond to W equals 2i. Our Riemann surface fixes our one-to-one problem just as our 2 complex plane solution did. Each of our 2 solutions on Z corresponds to its very own copy of the W plane. These are called branches. So our Riemann surface makes our mapping one-to-one just as our 2 complex plane approach did last time. But what about continuity? As we saw last time, a big problem with our 2 complex plane solution is that it introduced discontinuities. We constructed our surface in such a way that our colored path was continuous, but we encountered this weird self-intersection. So let's dig a little deeper. Remember the main idea here. Using our Riemann surface as the input space, or the domain, to our complex multifunction should give us clarity. So instead of drawing paths or shapes on our W plane, we should really be drawing on our Riemann surface. Drawing on 3-dimensional surfaces can be a little challenging, so we'll make use of a tool that wasn't invented until over a century after Riemann's death: a computer. Just as with our paper version, we'll start with our W plane lying flat on the ground, and place our Riemann surface directly above. Before we start drawing paths all over our surface, let's make sure we know what we're looking at. We're trying to understand the complex function W equals Z squared, or taken in the other direction, Z equals plus or minus the square root of W. The mapping between W and Z is the same in both directions. The visualization challenge here is that our mapping is 4-dimensional. Both Z and W have real and imaginary parts. Back in part 10, we called these X, Y, U, and V. What we're seeing when we visualize our Riemann surface is a 2-dimensional surface in 3-dimensional space. In this case, since we positioned our surface directly above our W plane, 2 of our 3 dimensions correspond exactly to the real and imaginary parts of W. We called these U and V. Part of Riemann's idea is that our 3rd dimension should represent the Z value of our function. But as we know, Z is a complex number. It has both a real and imaginary part, so there's no way to show both of these on a single axis. What's often done when visualizing these surfaces, and what we're going to do here, is simply pick the real or imaginary part of Z, and use this value as the 3rd dimension, the height of our surface. Here we're using X, the real part of Z. Doing this has a nice visual result. Each point on our Riemann surface lives in 3D space at a location corresponding exactly to its U, V, and X values. So each point on our surface represents a single solution to our equation, and 3 of the 4 values needed to describe the solution are represented by the point's location in 3D space. This is a nice result, but we must remember that this is not the whole picture. There's another variable, the imaginary part of Z, we call this Y, that is not included in our visualization. This becomes important when trying to figure out if we've actually fixed our continuity problem. If we follow a path along a single branch of our Riemann surface, we run into a bit of a problem when we hit this self-intersection. After all, which way should we go, up or down? To answer this question, let's try to figure out why our surface self-intersects in the first place. This intersection happens along the negative real axis of our w plane. Let's consider a point on this axis, w equals -1. Plugging in -1 for w yields two solutions, z equals +i and z equals -i. These two solutions are clearly different, but they have the same real part, 0. Since we're only visualizing the real part of z, we have no way of seeing that these are in fact different points. This is the danger of visualizing high-dimensional mathematical concepts. What we're really looking at here is just a projection, a shadow of our full four-dimensional surface. So our line of self-intersection actually isn't. This is exactly like the two-dimensional shadows of three-dimensional objects, giving the appearance that the objects intersect. There are inherent limitations to the types of structures we can visualize in the 3D space we live in. However, there are some very clever ways to get a feel for what's happening in our missing fourth dimension. One approach is to expand our visualization to include another dimension of human perception, such as color. We'll color each point on our surface with a color that corresponds to the value of the fourth dimension of our function, in this case the imaginary part of z, y. To do this, we need to decide which colors to map to which numbers. This is called a color map. Our colors now give us a nice idea of what's happening in our missing fourth dimension, y. If we look at our line of self-intersection now, it's much more clear that since our colors are different, our four-dimensional function actually doesn't intersect itself. The apparent self-intersection is just an artifact of our visualization technique. So as we follow paths on our Riemann surface, the right thing to do with these self-intersection lines is to ignore them. If we now follow our path around our surface, we see that it's perfectly continuous, even at our weird self-intersection line. Excellent. So that's great, we have continuity, but there's still one missing piece of the puzzle. What about the weird behavior we saw back in part 11, where some paths ended up in new locations and others didn't? Let's recreate these suspicious paths, first just on our w and z planes. Now, let's do the same exact thing, but this time using our Riemann surface to help us see what's going on. To keep our surface from getting too crowded, we'll choose one of our two paths to visualize first. Alright, ready? We'll draw the same exact paths on w and see how they show up on our Riemann surface as they are mapped to our z-plane. So why does our green path start out in one location on our z-plane only to end up in another? Simply because our green path leads us to the other layer of our surface. From the perspective of our w-plane, it appears that we've returned exactly to our starting point. But actually, we haven't. The w-plane is just a projection, a shadow. In reality, our path has led us to a completely different branch of our function, with different z-values. This, of course, is only half the picture. Each point on our w-plane has two solutions on z. This is why our single path became two paths back in part 11. On our Riemann surface, our second solution is a flipped version of our first. The important thing here, of course, is that for either set of paths, our Riemann surface allows us to clearly see that some paths on w lead to the other branch, and some don't. More specifically, paths that go around the central point on our Riemann surface end up on new branches. This point is called a branch point. Branch points occur wherever the two branches of our function have the same exact value, and can tell us a great deal about how our complex function behaves. For us, this is the point w equals 0. So our Riemann surface not only fixes the troubles we ran into earlier, but beautifully explains the strange path behavior we saw. And this is just the beginning. Riemann surfaces are a huge part of modern mathematics, and there's way more to say than we have time for here. Alright, we're finally ready to answer the question, what is this? Our entire discussion has centered around a single function, f of z equals z squared plus 1. And so far, we've looked at one way to visualize the Riemann surface for our function by plotting 3 of our 4 variables in 3D space. The two-dimensional plot we started our discussion with, the one most of us see in math class, only shows 2 of our 4 variables, the real parts of z and w. The surface we created back in part 1 is the result of including one more variable, the imaginary part of z, as the vertical dimension of our visualization. When we first saw this surface in part 1, many of you asked a very good question. If, according to the fundamental theorem of algebra, our function is supposed to have exactly 2 roots, why does our surface appear to equal 0 at way more than 2 locations? This apparent contradiction has everything to do with the shortcomings of living in 3-dimensional space that we've been discussing. When we visualize 4-dimensional functions in 3-dimensional space, we must remember that what we're really seeing is a projection, a shadow of the function's full 4-dimensional form. Let's have a closer look at our surface. In our opening shot, half of our surface was hidden behind our paper, and the colors we used were chosen somewhat arbitrarily to roughly correspond to the surface height. Now that we know a bit more about functions of complex variables, let's change the color of our surface to correspond to the 4th variable we were forced to leave out of our 3-dimensional visualization, v. Now that we have some idea of what all 4 variables are doing, let's look for the 2 roots predicted by Gauss. Remember, roots are where the output of our function equals 0. For this to be the case, both the real and lateral parts of our output variable w, u and v, must be 0. Seeing where u equals 0 isn't too bad. This is where our surface intersects the z-plane. Now, where does v, the imaginary part of our output variable w, equal 0? If we look at our color map, this should be where our surface is green. It's difficult to see exactly which shade of green corresponds to 0, so let's add a blue line to our surface where v equals exactly 0. Now, if we look closely, we see that both the real and imaginary parts of w equal 0 at exactly 2 points, positive and negative I on our complex z-plane, exactly as our algebra predicted. We have finally found our missing roots. So our friend Gauss was right all along. Our function does have exactly 2 roots. Of course, finding these roots took some effort. We had to journey deep into mathematics and ask ourselves what a number really is. This led us to the strange but necessary conclusion that the numbers we should really be using in algebra are the 2-dimensional complex numbers. This result dragged us down deeper into the 4-dimensional world of complex functions and Riemann surfaces. When we finally emerged, we saw that the algebra many of us learned in school is only a shadow of an elegant, powerful, and higher dimensional mathematics that has everything to do with the numbers that have been given the terrible name imaginary. Thanks for watching.